it's brown.
Let's see mom's first reaction.
I come here along with my wife and Subarna once every week, especially on the weekend, at Brown University to visit my elder son, Raf. He is a graduate student in physics at Brown University. So this is an opportunity for everybody to listen how the life of a graduate student of an Ivy League university like Brown. Raf, how many classes are you taking?
2 classes.
2 classes. You are taking advanced quantum mechanics with Alexander, Professor Alexander, and you are taking advanced statistical mechanics with Professor
Yaveki.
Iaveki. So I had an opportunity not only once but twice to match with to solve problem with Professor Kosterlitz, Michael Kosterlitz, uh, here at Brown University. So today you're gonna share this experience with us. First, start with your experience with Professor Alexander in quantum mechanics class.
Absolutely. So in our first class of advanced quantum mechanics, we derived the Klein-Gordon equation, which was the first historical attempt to combine Einstein's special relativity with Schrodinger, Dirac, Pauli's theory of quantum mechanics. And
why special relativity? Why not the general relativity?
So special relativity is the first step before general
So
relativity.
special relativity,
So
Einstein derived in 1905.
that's right.
Okay. So and then general relativity he derived in 1915.
Yeah.
Okay.
So we don't have a theory that combines general relativity with quantum mechanics to this day. But even before you do that, the prerequisite to a theory of quantum gravity is the special relativistic theory of quantum mechanics. So that combines special relativity with quantum mechanics. So
So what are the differences between the special relativity and the general relativity?
So special relativity is the theory of what happens when you move fast.
Move fast without accelerating.
That's right.
Okay. And general relativity?
General relativity is the theory of what happens when you're big, when you're heavy, when you have
and when you also accelerate.
Yes, it can account for acceleration. Yeah.
Okay, so these are the differences.
Yeah.
Okay, so that's the advanced quantum mechanics that you are taking with Professor Alexander. You also took the quantum mechanics 1 at at NYU and and graduate quantum mechanics at City College of New York. Now let's talk about statistical mechanics. What is statistical mechanics? And I heard that statistical mechanics, Brown University pioneered statistical mechanics. Tell me some historical background.
So that's right. First of all, what is statistical mechanics?
Right.
So the word statistics is in the name, meaning it tells you something that it's the physics of statistics,
Right.
but it is not that boring. The name does not give the true impression of the subject.
Okay.
So statistical mechanics explains everything from why does ice melt into liquid, why does liquid.
So it talks about the phase shift.
Phase transitions are one big part of statistical mechanics.
Okay.
But they're not the only part.
So phase transition, for the high school student can understand phase transition because they studied heat current.
Yeah.
And is also go as big as the graduate school, right?
Yeah.
And the cutting edge physics has to do with the phase transition.
In fact,
he won the Nobel Prize, the phase transition of a black hole.
Right.
Yeah. Well, before we go to him, let's add more information of how Brown University pioneered statistical mechanics and your class.
Yeah. So for the first 20 minutes of advanced statistical mechanics, Professor Yaveki talked about how statistical mechanics was born here in Brown.
Right.
So the two main pioneers of statistical mechanics were both professors here at Brown in the 1930s.
Right.
So one of them is Lars Onsager, who won the Nobel Prize in Physics for exactly solving the two-dimensional icing model in 1944. Nobody had ever solved that problem before, and when he solved the problem, people called it a physical tour de force. So he attacked the problem from all sides using group theory, renormalization method, all sorts of things. So he became the first person to solve the 2D icing model exactly. By exactly, I mean he did it with pen and paper, not a computer.
Mm-hmm. So he was a theoretical physicist and he did not
Yeah.
do the experiment.
Mhm.
He proved that.
Yeah, that's
Okay.
right.
Was there any experiment?
Experiments later confirmed that his solution was exactly correct.
That's why he won the Nobel Prize.
After that, he won the Nobel
Okay.
Prize.
Now we are talking about now the cutting edge research in phase transition, and that's why Professor Kosterlitz won the Nobel Prize in what year?
2016.
2016, very recently.
Yeah.
Now you met with him not only once, twice. How did it go?
So it was, hard to describe with words.
Okay.
So it was a surreal experience.
How did you introduce yourself?
So I had sent him a few emails over the summer.
Did he reply?
He replied to one of them.
Okay.
He said that he would be willing to be my advisor.
Okay.
But I think that he was probably not a uh, he he didn't recall that email when he spoke with me.
Okay. So he's now 81 years old.
He's 81 years old.
Okay.
So I introduced myself as Rev Bari, a City College graduate,
Right.
and I published two papers, uh, all by myself in geometric optics.
Right.
And now I want to work on black hole phase transitions, and I was wondering if you would be my mentor.
Right.
And he said that at this age he doesn't want any new commitments, but if I have any questions, then I can go into his office.
Right.
And his office is exactly here, one floor down, on the third floor.
Yeah, Brown really celebrates his legacy. As you see, our behind
Absolutely.
is the over there.
That's right. And on the first floor, they also have this
That is okay. Wow.
poster. So yesterday I had recalculated the derivation for the one-dimensional Ising model, and I had a few questions. And so I went to the third floor.
What is one-dimensional Ising model?
The simplest explanation of how magnets work.
Okay, all right. How magnet works?
A magnet works because an atom is like a very, very tiny magnet.
Okay.
Why is the atom a very tiny magnet? Because if you zoom into the atom has three main subatomic particles: protons, neutrons, and electrons. Forget about the proton and neutron. Let's talk about the electron. The electron is very, very weird. If you put the electron in a box and you measure the angular momentum of the electron, you get a number.
Those electron has to be aligned at the same direction to be magnet.
Yes, that's right.
If those electrons are not aligned to the same direction, they are not magnet.
Then their spins will cancel each other out.
Okay. So how can you create a magnet when an ordinary metal, right, is not magnet? How can you make an ordinary magnet? What they call it, alnico. How can you make any member of alnico to a magnet? So what is the process?
The basic idea is that somehow you have to align all the spins of the electrons.
How do you do
in
that?
The alnico. So to do that, you need to apply an external magnetic field.
Right.
A very weak external magnetic field.
Can this coffee cup create a magnetic field?
No. Well,
why not?
First of all, this okay.
Because if you put a member of alnico family over here, the member of alnico family will feel no attraction to the, because it doesn't create the magnetic field. It's not a magnet because it doesn't create the magnetic field.
And not only that, but applying an external magnetic field will not work for everything. For example, if I apply an external magnetic field, I know for sure this will not be attracted to a magnet. Now, why is that? Because this coffee cup is
I have
made
actually too.
of so it's made of, I suppose this is plastic or something like that.
Yes.
Now the elements that plastic is made out of, they have a net spin of 0.
Right.
Why do they have a net spin of 0? Because all the
electrons is spinning, they cancel out because they are not aligned at the same direction, and there is no way you can align them at the same direction.
That's right. The reason why is because the electron spins, they pair in opposite directions. Why do they have to pair in opposite directions? Because of the Pauli exclusion principle.
Right.
Says that electrons that are occupying the same orbital have to cancel out.
Right.
So most elements, there are 118 elements in the periodic table. Most of them,
from hydrogen to organism,
right, will never be magnetic. The reason why is because their spins will cancel out. So for example, if you have a carbon element, and you have all of the electrons in the carbon element spin up, spin down, spin up, spin down. All of those spins will cancel each other out, give you a net zero spin.
Okay, therefore this is the
Yeah,
spin is zero.
spin
Is
is zero.
because
Yeah,
they cancel out each other.
yeah.
But this is not the case for a metal.
No.
Any member of alnico family, you can if you bring it to a magnetic field, it becomes a magnet.
Right.
And
And why is that?
because the electrons will align in the same direction,
Right.
and
And
even if you remove the magnet,
right.
those electrons will remain aligned in the same direction, making it a permanent magnet.
Right. But not only that, but some of the electrons are unpaired in their orbitals. So, for example, if you have 5 electrons, maybe 4 of them will be paired, but the last one will have no partner. So the last one will contribute to the total spin of the atom. And not only that, but no matter what kind of a magnet you have, no magnet is truly permanent. That's actually what Pierre Curie discovered. Uh, and according to the 1D Ising model, if you put a fire, if I don't have a magnet here, but if I had an alnico, metal, and it was magnetic, if I put a fire under the magnet, then it would, at a certain temperature, it would lose all the magnetic properties because the temperature starts to cause the spins to become random.
Right,
And
right. The kinetic energy increases,
right,
and
that's
then
right.
yeah,
And
random, and then what happened after that?
so at the Curie temperature, the
Yes.
critical Curie temperature, the magnet dies.
What Curie temperature?
So it depends on the element.
Okay.
I don't know the exact Curie
I
temperature
see.
for
I
an
see.
element.
I see.
It
I see.
depends on
It's
the element.
opposite to the Bose-Einstein temperature, I believe.
Well, Bose-Einstein has to do with making things, making
Very
something
cold.
very cold,
Which is almost
near
zero,
absolute zero.
near absolute zero
Yeah,
Kelvin.
yeah,
So we are talking about like almost 0 degree Kelvin,
yeah, yeah.
right?
That's right.
Negative 273 degrees Celsius. I don't know.
Yeah,
Yeah,
that's right.
yeah.
That's
Okay,
right.
which
You
is
actually don't need exactly zero.
that's right.
Mhm.
Yeah,
Yeah,
I can only imagine negative
yeah.
273 degrees Celsius. I mean, people will immediately die. Yeah.
Long before that.
Okay, so this is icing model.
Yeah.
So what is icing model again?
The simplest explanation for why magnets work.
Okay, all right. The magnets all the way goes back to who discovered magnet? Do you recall?
I well, Michael Faraday uh,
Michael Faraday
explained
was
why
the.
fields work,
That's right. Michael Faraday
but
was the one who used that properties. Uh, why? Well, it's actually started with um, Orsted, right?
yeah,
Orsted, while teaching, he realized that when the current carrying wire, right? What
deflect the
happened?
compass needle.
That's right. The current carrying wire, if you bring the magnet close to the current carrying wire, what happened to the needle?
Yeah, the compass needles will go clockwise or
Clockwise,
counterclockwise
depending on the direction of the current. So he discovered that, and Michael Faraday um, took that idea and make it more useful. But magnet invented a long time
before that. There were things called magnetites, natural magnets in nature. There are rocks that actually in nature, rocks that tend to stick together, called magnetites, made of iron.
So the magnet
The-
actually invented by Thales.
what?
Thales.
Oh,
So
I don't know.
Thales, you are. Do you recall any contribution by Thales in math?
Who's
Thales was a Greek scientist, pre-Socratic scientist, who discovered magnet.
oh,
So he discovered magnet. He actually discovered magnet by using ember. Can you summarize your experience, weekly experience for our audience
my weekly experience at Brown.
at Brown?
So it was full of academic discovery and excitement, and it's I read a quote somewhere that it's a unfair advantage to surround yourself with the greatest minds in physics. It's an
Unfair advantage. Well,
you
maybe
cannot.
you deserve it, so it's not so unfair.
Yeah,
You work so hard
that's right.
to
Yes.
deserve it. It's not so unfair, but it's always
That's
good to be humble. And
Yeah.
it's always good to keep yourself grounded.
That's right.
What part of brown life you love most? I believe dining.
Dining is a part of it. Let's see. I'll take you through my day.
Why should one go crazy to
Yeah.
become brown student? Is it because of physics
Well,
department? Is it because of dining? Is it because of anything else?
the simple answer is
I forgot to
you.
ask you one thing. I
Yeah.
remember you shared that one father.
Oh,
Uh,
yeah.
yeah,
Yeah.
you shared that story with our audience.
Sure. So I was walking to Brown.
You encountered by a father and son.
Yeah. So I was walking to Brown and I saw a father and son who looked lost.
Okay,
And I asked them, "Are you lost?" And they said, "No, we're actually touring the
the
campus."
campus, right?
And the son said he was gonna apply.
Yeah,
And I said, "Okay, sure." That's all I said. And the father said, "Do you have any suggestions
right,
for places we should look at?"
right,
And I said, "I'm going to the Department of Physics. If you'd like, you can come follow me."
right.
And the father said, "If you don't mind, that would be great."
Mm.
And so as we were walking, the father asked me, "You must have been excellent in high school to be accepted here." And I said, "No, I'm a graduate student in physics. So I did my undergraduate somewhere
A
else."
city college of New York,
That's right.
not so big school.
He asked, "Where did you do your undergraduate?" And I said, "You won't know. It's City College of New
Right.
York. It's a school in New York."
So
And he said, "Okay." And
that gives hope for him. You
that's
can
right.
you can go anywhere, but you still make it to Brown.
That's right. So the son and father asked me lots of questions. What is it like to live at Brown, to dine at Brown, to study at Brown? They were, very excited. So I led them to the Barris and Holly building, the
The
department
physics
of
department.
physics department. And so I said, "All right, this is it." And from the outside, we know it doesn't look, you know, it looks pretty
It looks
normal.
nice,
It
yeah.
looks nice. And the father,
And there is
the
a
son stood
there
there,
is a there is a big
Mobius strip
Mobius
outside.
strip outside. It
Uh,
looks nice enough.
yeah. And so I said, "If you'd like, I can show you inside." Uh, and they were like, surprised and happy. So I swiped my ID, unlocked the door, and brought them in. And I showed them the lobby with Aristotle's four elements, and I showed them this physics floor, fourth floor.
They told you they are from Zurich.
They told me they were from Switzerland. That's right, Zurich,
That's right.
Zurich.
Yeah, so very
And
good.
yeah,
And
they actually took. The father asked me to
picture
take a picture in
picture
front
in
of
front
this.
of the Nobel laureate. Coming up from Barry's and Holly Department of Physics at Brown University. You guys take care. Bye bye.
Bye bye.